Hello, and a warm welcome to everyone attending this session. I am 𝗪𝗘𝗓𝗏, Assistant Marketing Manager at Shree Rapid Technologies. I'll be your host and moderator for this session. Let me start with my presentation. Let us start with the webinar. We are thrilled to bring you this session in collaboration with our OEM partner 3D Systems on the webinar topic, the productivity of light projection, the quality and reliability of SLA. So before we move ahead, here's a quick look at the agenda for today. So we will have a quick introduction to Shree Rapid Technologies, and then we'll have the main session by our keynote speaker Sam Green from 3D Systems, followed by an interactive poll and a Q&A session. So before we dive in, allow me few minutes to introduce you to who we are and what is Shree Rapid Technologies. So incorporated in 2007, we are a complete digital manufacturing company providing end-to-end solution in additive manufacturing industry. We are one of the leading solution providers with around 17 years of experience and 850 installations across India. Dedicated team of engineers, and we have a presence pan India. We provide digital manufacturing solutions in all type of 3D printing technologies. Also, we have a digital manufacturing workflow from reverse engineering, metal or powder atomizer, 3D printing, inspection, and post processing. These are global leaders we are representing in 3D printing and scanning technologies, and we support presence across multiple industry, aerospace, automotive, jewelry, name it, and we are there. Our Customer Innovation Center in Mumbai are equipped to support both metal and plastic application, enabling hands-on experience and solution development. With that short introduction, let's move to the heart of today's session. It's my pleasure now to welcome our keynote speaker, Sam Green, Director of Platform and Product Management at 3D Systems, a seasoned product marketer with over 15 years of international experience in 3D printing industry. Sam has led platform and product management at 3D System with many other key roles in the industry. He's known for making complex technology easy to understand and build strong, impactful brand strategies. So thank you, Sam, for joining us and having this session. To go further, Sam, the screen is all yours.
So yes, the name of the presentation, the productivity of light projection, the quality and reliability of SLA. This is all about the PSLA 270 3D printing system. Thank you very much for that nice introduction. My name is Sam Green. As you heard, I'm the product manager here at 3D Systems for SLA, PSLA, and Figure 4 systems. And today I'm going to talk to you a little bit about the PSLA 270, which is a new product that we introduced to the market at Formnext, just the recent Formnext here in the end of 2024. So what is the PSLA? It's a production-capable mid-frame projector-based SLA solution. And it does include a cure solution, materials, and software. And essentially it combines the productivity and reliable quality of SLA with the speed of what we used to call, or what we call, light projection or DLP technologies. So the PSLA 270 is, first of all, a compact, very powerful production system. It's a mid-frame solution. And if I was to say what's unique about the PSLA 270, it's that we've managed to include all the very best attributes of traditional laser-based printing, or what we call SLA. And as I will show you shortly, with all the best attributes of light-based projector imaging technologies, sometimes referred to as DLP. So as you can see in this schematic that I have here, this printer has a unique configuration. So we have the projectors, we have two projectors, they're fixed at the top of the printer, and they project their light source down into a traditional SLA vat of resin. And the system has a recoater and a displacer and forks and a platform, and that platform moves down as that part is built in the resin. And this is what the printer itself looks like. Some key features to take note of. First of all, you've got these high-powered projectors, two high-powered projectors that are 7 watts each. These have very advanced optics, and it's the combination of the optics and the quality of the projector that really delivers a lot of the quality and amazing surface quality that you will see on the parts that we show you. So two 7-watt high-powered projectors delivering 90 micron pixel sizes, native 90 micron native pixel sizes. The system is a 405 nanometer wavelength system only. We don't have any other, we don't do 385 at this point in time, so it's just a 405 nanometer wavelength, and that has implications for the materials that we're using that we'll go into shortly. With these two projectors, we're able to deliver essentially 5, sometimes even 6 times faster layering times compared to laser-based technology, and I'll show you a graph of that shortly. We've got the two projectors allow us to deliver a really good mid-frame build size. It's 242 by 265 and 300 millimeters deep. We have a new dual rail recoating system. So it's not a cantilever design, it's an all new design. It's very robust, it's very accurate, it should deliver consistent performance over time. As I mentioned, the 405 nanometer light source is optimized to run our figure 4 set of materials. Now, if you're familiar with figure 4, then you know what I'm talking about. If you're not familiar with figure 4, these are really the best in class industrial resins for high temperature, high performance, production, prototyping, and additional special applications. And many of these materials are already qualified to run on the PSLA 270. In addition, we have a roll-in vat that is mounted to the frame. I'll show you that in one of the upcoming slides here. It's a really nice design, and it really gets over some of the historical SLA problems of switching materials easily. So this really does allow quick material swap overs. We've got a brand new user interface and a UI screen, a very nice size, 10-inch HD touch screen. What's interesting is you can swap it to either side of the printer. We have a built-in camera, so you've got your remote monitoring enabled with that. We have an auto-filled material delivery system that I'll show you shortly. It's located in the bottom of the printer, and that will automatically pump your resin and keep your vat filled. Also, this whole system is really designed as an extremely versatile system, designed to have a small footprint, fit in any space. I'll show you some interesting information on that shortly. And it's a small footprint, as you know, but don't be fooled. I mean, this is a very sleek mid-frame design, but it's really a force multiplier in terms of its ability to rapidly produce excellent quality parts and production capable parts. So, as I said at the beginning, this is a very powerful and productive solution for effectively scaling from prototyping to production. But what does that mean in practice? So I think in practice it means you need really the following 4 qualities to succeed. First of all, you need high first article success rate and part quality. This means the ability really to produce your parts successfully the first time around without experimentation. Second, you need high performance engineering materials. We'll talk about that with our figure 4 line of materials. Now, this has always been a traditional weakness of resin-based printers in the past. But remember, we're really working on a revolution here in resin printing. And materials is at the forefront of that revolution for 3D systems. Third, you need dimensional accuracy and repeatability to satisfy true manufacturing requirements. And fourth, you need speed or productivity or throughput, however you decide to term this. But really, it's the ability to ship your parts within a very defined and limited time frame. Okay, so let's see how the PSLA 270 answers each of these 4 key requirements that are essential when you're moving from prototyping to production. So please ignore the person in the photograph. I don't know who it is. It's some people say it's me, but I don't know. Anyway, first of all, the PSLA 270, as I mentioned, has an unconventional layout. So the projectors are at the top, projecting down into that vat of resin. So this top-down approach delivers many of the key advantages that made SLA the staple of 3D printing for many years. Remember, with the PSLA 270, we're taking the best of SLA and the best of light projection and avoiding the drawbacks of either of those technologies. So this is an example. So you see on the left, I'm holding a typical DLP, on the left-hand part of the screen, I'm holding a typical DLP printed part on its supports. And you see that those large parts are printed basically hanging. And of course, the larger the part, the more supports you're going to need to support it. Whereas on a PSLA, on the right-hand side of this photograph, you see 2 parts, the same parts, sitting comfortably on a tray, and that is the orientation that they're built in. So obvious from the very beginning that there are advantages to the PSLA when it comes to building larger, bulkier parts. So parts are built within the resin. They're not hanging in the air against gravity. Let me just run this short time lapse just to show you what it looks like as it comes out of the printer. There you go. So again, as I said, this has lots of benefits, especially to larger prints, such as these parts that you see in these photographs. One of the main advantages here that you're getting less distortion on larger parts than you would if such parts or other parts were hanging upside down in the air. It also means that you have fewer supports and they can make do with also thinner supports. So for example, these are parts that I was handling for the making of a PSLA 270 film. And I found that it was extremely easy to remove these particular parts from their support space. In most cases, I just had to do a single twist with my hand and the parts came off really cleanly with basically almost no supports attached whatsoever. So a very, very quick and easy process to remove those supports. Now, another big advantage here, now this is an advantage versus DLP systems, right, is that you don't have to deal with membranes. You don't have to deal with films and replacing films and breakages of the films and the stickage of the membrane to the parts. None of that is relevant with a PSLA. In fact, there is no barrier between the light source and the surface of the resin. Okay, that's an important point. With DLP and other technologies, sometimes you have multiple barriers between your light source and your resin. This one has none. And of course, when you build, especially inverted upside down with a membrane in between, it introduces all sorts of distortion forces from the peeling of the membrane away from each layer. And this effect, added to the gravity on bulky parts, and you can get significant distortion. So, and this is an important point, and we see this in the industry as a whole. So, DLP or LCD type systems, there's a lot of them out there on the market today. They can work well with smaller sized parts or basic prototyping, but the issue is these type of systems do not scale very well to larger parts. Okay, so there is an inherent trade-off between larger and larger film or membrane-based systems that we see on the market at the cost of part quality, part accuracy, and repeatability. So with the PSLA 270, this is not the case at all. And this is one of those, factors that really separates this system from some of those, if you call low-cost systems that seem to have bigger and bigger film membranes. And another point, when you do print these larger parts, for example, if you're printing them the right way up and they're supported on a base inside the resin, as you can see here, these PSLA parts are built, nicely upright. There's no chance of these parts falling and damaging hardware such as the membrane or even the projectors. Remember, the DLP systems have those projectors underneath, right, underneath the part. So there is a chance those heavier parts can fall off of their supports, do quite a lot of damage to expensive hardware underneath, whether it's projectors and at least membranes as well. So, all of these points together is why we believe the PSLA delivers exceptional first article success. And in fact, in recent tests, let's just show this. So we did some recent tests, and we printed these 12 files and builds that you see on the screen, and every single one was successful out of the printer the first time around. Okay, so that is a key point. Again, if you're printing on some of these cheaper systems, you're going to have to go through quite a lot of an experimentation with the files in order to successfully print your parts the first time around. With PSLA and all of the points that I've mentioned, we have a much better chance of first article success, less time, less labor involved, more production readiness. Now, if you recall, I mentioned there were 4 items that you need really to transition successfully from prototyping to production. The second thing you really need to successfully transition is high performance engineering materials. And this is where standard epoxy and acrylate resins have been traditionally weak, right? Especially in the SLA space, also the DLP space. And you can see an example here in this chart. This shows, this is an accelerated indoor aging chart for one of our older materials. And this shows, this is a typical, it can be an epoxy or an acrylate resin. But this shows you what happens to the elongation at break of the material as soon as it leaves the printer. So you can see as soon as it's out the printer, these parts continue to cure in UV light, in natural UV light. They are affected by humidity, and you see that their elongation at break rapidly drops immediately as soon as they're in your hands. And within a very short time, they are only at a fraction of their original strength. So, in this particular case, this particular material falls to just 16% of its original elongation at break within less than 100 hours, right, in indoor conditions. And this is indoor stability testing. Now, imagine how much worse that would be in outdoor aging stability, where you have harsh light and humidity. So now compare that chart, keep that chart in your mind, and compare that to what we have with our figure 4 materials. Okay, these are all figure 4 materials. We're using here an example, the figure 4 Flex Black 20, which is like a polypropylene-like snap fit material. And we've tested here the elongation of break, the impact strength, and the tensile modulus in all of these charts, right? Now, we've been working on these resins for a number of years now, and we've reached the point where these resins are really able to remain environmentally stable up to 8 years in indoor conditions and up to 1.5 years, and in some cases I think it's even 2 years for some materials in outdoor conditions. So you can see clearly from these charts that if you follow the green lines, right, there's no sudden drop-off in mechanical performance all through the 8 years of this indoor test. And these are not subjective tests, by the way. These are not tests that we've designed only on our own. These are per the ASTM, the American Standards testing methodologies. So these results, and actually we provide these graphs documented in every single one of our Figure 4 material data sheets. So if you go online to 3dsystems.com, you can find in our materials section all of the Figure 4 materials, and you can download those data sheets. Each one of those data sheets is like 6 to 8 pages long. Why is it so long? Because we have all of this information clearly laid out for users. And this is one of the big differentiating things between us and any competitor out there. I don't think I've seen any competitor that has a 6 to 8 page data sheet for their materials. So all of their testing can be taken with some grain of salt. These are more objective standard tests that you can really verify and use for true production applications. So when we first released our Figure 4 materials back in, I think it was 2017 or 2018 now, we began our journey with just 3 basic materials. Now, all of that has really changed in the last few years. We're now at over 25 materials. And of course, when we started, those materials were just basic. They were not environmentally stabilized. Now, almost every single material we release has environmentally stabilized testing. And we've got a range of different materials to suit real applications for real manufacturers, including rigid materials, tough, durable, high temperature, biocompatible. A lot of our materials are biocompatible for medical and dental, a range of specialty materials that are automotive fluid compatible, chemical compatibility. We have a range of, I think the best range of flame retardant materials in the industry, with all of them have V0 flame retardant ratings, and a range of basic colors and transparencies. We're not fully there yet. We need more, but we're working constantly on releasing new materials. And I think 3D Systems is one of the largest investors in R&D for materials in the industry out there. So, more new materials being released every year, with some exciting announcements coming very soon. And by the way, you can see here, these are all photographs that I've taken of parts in my hands. These are right directly off of the printer. I haven't changed anything. I haven't sanded or polished or lacquered any of these parts. This is how they come off of the printer. So back to our list. So we mentioned a couple of points. Now the third point that we need for transitioning to true production applications is real manufacturing levels of dimensional accuracy and repeatability. Now, our internal testing shows a capability of more than 99.99% of the printed parts are repeatable within a plus or minus 100 microns. And this is across printer to printer, and we've also done the same tests across platforms and between parts on the build, so quite conclusive. In addition, these parts, and indeed all the parts you see in this presentation, like this one, these are right, you can see the quality of these parts. Again, they come directly out of the printer with no polishing or sanding. This is how they look on the platform immediately after they've been printed. So until now, all of the points I've mentioned are really points that are what we gain from our SLA heritage, right? But SLA also has some drawbacks, and we mentioned some of the primarily one of the main drawbacks of SLA is speed and scalable productivity. Because SLA is using lasers that are vector-based, your draw time, and actually I've compared it here on this chart. So the draw time of the laser is in blue in the bottom bar, right? So your draw time makes up about 85% of your entire layer time for SLA. And it really is the major limiting factor to how fast you can go, right? And the more lines you need to draw, the slower your build will be. Okay, so for example, in that previous slide with all those small connector parts, right? Lots of lines and significantly more build times. However, the PSLA system, right, is based on raster-based printing, not vector-based printing, right? With those two projectors at the top, you are curing an entire layer at a time. So as I mentioned maybe at the beginning, your print speeds are going to be 5 to 6 times faster than traditional SLA in most cases, right? And the more parts you add to your build tray, it makes no difference to your print time. So that's very, very important if you're a company that wants to scale into batch production, and time is one of the limiting factors. So as I mentioned, you'll typically get the most speed advantage compared to SLA when you print smaller builds with more vectors. So for example, we just did a quick test. These 96 connector parts that we have in the photograph, there's 96 of them, printed in ProBlack 10 material, which is our standard prototyping and production material. These were printed in just over 1 hour on the PSLA 270. And typically on our mid-frame SLA, this would normally take about 5 hours, sometimes more. So big, big difference. But even on larger parts, right? So for example, the part I'm holding in my hand there, you get real speed and productivity advantages also on larger parts. So in our internal testing using 6 different materials, I've got them listed in this table here on the left-hand side. These are the 6 different materials we used. We printed a 250 millimeter tall part. You can see the layer thicknesses here. The layer thicknesses vary somewhat. Some of the whiter materials have require thinner layer thicknesses just because of the reflectivity of the material. So you can see the layer thicknesses, the build times, and the final part in hand time. The part in hand time is the part once it's out of the printer and it's been post-processed and it's delivered into your hands, right? So what we find here is that 4 out of these 6 materials, these tool builds, were able to be placed in your hand, complete and ready to ship within 15 hours. 15 hours, right? So why is 15 hours like a sort of benchmark? Because that is the typical time it takes for an overnight build window, running from say 5 p.m. in the evening. You start your build, and then coming back at 8 a.m. the next morning, right? And this is critical for industries like service bureaus, where you need to start a print late in the day, it's maybe towards the end of the day, and you want to come back in the morning and you want to be rest assured that your part has not failed overnight, it's not fallen off the platform, it's not any other things that have gone wrong with it, and it's ready to come off and it's ready to be post-processed and delivered to your customer before lunchtime. So some of the other production benefits worth mentioning about the PSLA 270. So first of all, I mentioned at the beginning, material changeover. So with the PSLA 270, this has never really been easier. So we've designed a mobile cart that carries your vat. You can see it here on the left-hand side. It's got a handle, which is labeled A, and those are the wheels labeled in B. And what happens is you push this vat into you open the door, you open the bottom door of the printer, you push the vat carefully so the resin doesn't spill, you push it carefully into the printer and you lift up that handle. And as you lift up the handle, the wheels come off of the ground and you can see there's datum points on the side of this vat, and the datum points are engaged and attached to the frame. So your vat is stabilized to the frame to ensure that it's not, otherwise it would there'd be a detrimental effect to accuracy if your vat was free floating separately from the frame. So that the vat is attached to the frame with the handle. And then if you want to take it out again, it's a very simple process just to lift that handle down and wheel out your vat. And typically you'd have another vat sitting on the side with a different material. All your wet components come off by hand, go into that vat very easily. As you can see in the diagram here, the forks, the displacer, and even the recoater come off just with a single hand movement without any special tools required. They come off of the system, they can go into the vat, all your wet components stay together, and you can have another vat on the side ready to push in and you can do a material change within about 3 minutes. In addition, so what we have between the legs of that vat, and you can see it here with the letters C and D, you have what we call our MDM, material delivery module, and this consists of a newly designed 9-kilo bottle. You can see it's a square bottle with a lot of resin in it, 9 kilos, and that sits directly into that resin bay, which is labeled D. And then you just close that drawer nicely, and then you have your auto pump that keeps the vat full and ready for long production jobs. You also have the option of hand pouring as well. Everything is via the UI screen, so you can choose whether to use the MDM or you can go for hand fill if you prefer that. Okay, so as mentioned earlier, with the PSLA 270, you have 2 HD projectors. Now, those projectors do not work separately. They work together to deliver the large mid-frame build volume of 242 by 265 and 300. Now, as well as allowing you to build thousands of smaller parts and large parts very quickly, as in this photo, it also helps with your first article success, because as you now have really greater freedom than you would with a smaller system, you have the freedom to orient your parts in the most optimal way on the build platform to ensure that your parts come out successfully the first time round. So that's a very important point with acrylates as well. Acrylates need to be treated slightly different from epoxy materials. So the orientation of those parts it's useful to be able to have flexibility to change the orientation of those parts and play with that as you need to on the build tray. Just a point, compared to our previous Project 6000 SLA system, our build volume in this system is 1.5 times larger, and the system footprint is actually about 30% smaller. So a smaller printer with a larger build volume than what we've delivered previously. The dual rail recoating system further enhances the part quality. It's a more precise and reliable dual rail design rather than the cantilever design which we've had on some of our other systems. It can be rapidly removed and reinstalled by hand. It's got 2 hand levers that basically allows you to snap off the recoater, snap it off, snap it on, and it really requires minimal recalibration once you've taken that off, allowing you to do a very fast material changeover. I think the calibration really is a matter of just a few minutes instead of hours. Now, as I mentioned, this is a very versatile system with a compact footprint. As you can see in this diagram here, all of the side panels on the printer can slide on and off. Again, you don't need to undo any screws. They all come off really by hand in a simple process. And the doors can be used. They're the same doors on either side of the printer. So you can take these off. You can manage side access. You can have a robot, for example, accessing from the side, whereas humans would come from the front, or vice versa. And it gives you much more flexibility in your total factory floor layout. You know, how you orient these printers in awkward spaces. So I think this really is a system that's equally at home in tight and awkward facility layouts. Another important point, the front door is reversible. So as you can see in the bottom left photo, you can position the door to open from the right or the left. Again, helping you if you have an awkward corner that the printer needs to fit into. And the same with the UI screen. The UI screen can bolt onto the right-hand side, or it can bolt onto the left-hand side. So you can really orient 2 printers quite close together, making sure that the doors open and in different directions, and the UI screens are mounted antagonistically. Another interesting thing, we made sure in the design that this printer can fit through a standard 30-inch office door frame. In fact, we wheeled it through the smallest door that we had in our facility. It was a standard 30-inch. We turned it a little bit sideways, but we did not tip the machine over. So it went in through the door on all four legs without tipping the machine over. We just angled it a little bit on its side to make sure the UI screen could get through as well. But easy to get through. A 30-inch door frame with two people. So to deliver the sort of part quality you see here out of the printer, and again, this is out of the printer, right? If you look carefully, I don't know if you can see it on this part, but there are some support scars on the side of the part where we just ripped off the supports. So this, really this is one of 3D Systems' specialties. Our internally developed image processing software, we're able to automatically adjust the system's pixel edges. So I mentioned it's a 90 micron native pixel size, but really, we're able to significantly deliver really, really good quality results, even with those 90 micron pixels, using our edge grayscaling techniques. And the result is extremely high quality, production grade, good looking injection mold quality parts. I don't think there's many systems out there that will deliver this quality with these material chemistries. So to summarize, the PSLA 270, as I said, produces exceptional quality parts, exceptional accuracy and throughput. And all of these advantages I've outlined here are really key factors that separate the PSLA 270 from the many other systems out there today. Speed, part in hand times, first article success, dimensional accuracy, repeatability, material mechanical performance. All these factors come together to answer the needs of true manufacturing batch production. But don't think that's necessarily an easy achievement, right? In order to guarantee our first article success and part quality, all of our materials and our print process and our image processing software and our printer hardware have been developed in-house, and then those efforts have been seamlessly integrated together into the solution we see before us, right? So it's actually a culmination of a lot of work. It's also a culmination of 3D Systems' many years experience, both in projector printing and in SLA printing, and all the lessons that we've learned there. And I think 3D Systems is really uniquely placed in the market to deliver, solutions to complex customer challenges. And I think there are very few other vendors out there today that can offer the same. And lastly, make sure you visit the Customer Innovation Center in Mumbai. And there you'll be able to benchmark your 3D printed parts with the team at Shree Rapid. Thank you for listening. I will leave it open to questions. I'll take it back to you.
Thank you, Sam.
Pleasure.
Thank you for that deep and engaging session. So we would like to start with our question answer. So submit your questions in the chat box or the Q&A section. And so Sam, I will read out the questions, and Rohit will assign you the questions as well.
Okay.
So the first question is, do we have to buy the resin for you, or is it open to the third parties?
This is designed for Figure 4 resins only at this point in time.
So the question is from Prakash Vipai from India. Can we use this machine to print high-end jewelry, carat gold in 9, 10, 14, 18 and 22 carats?
You're asking if you can use this printer to produce jewelry parts. We have a jewelry resin. In fact, we have a number of resins that may be useful. I think we need to start by benchmarking. We've done some preliminary tests for jewelry parts I think they were fairly successful. So I think that's a question for benchmarking.
Okay. So the next question is, secondly, what the surface RF of the printed parts?
What is the, sorry, the what? The surface RA. Oh, okay, the surface RA. So it varies a little bit, but on the top facing surfaces, we can get down to quite a remarkable number, 0.25 RA on the top facing surfaces of the parts. Some of the side faces, I haven't got a full test, but I printed parts where we've got anywhere between 2, 5, and 8 RA on the side facing surfaces, but we can really get up down to 0.25.
Okay. The next is, can you print silicon material?
Right, so we have a special material called eggshell molding material, and this is basically a cavity. You print the cavity on the PSLA and you inject it with true silicone. So this is a fantastic solution that a lot of our customers are using, particularly in the motorsport F1 industry. They use this solution all the time. It doesn't use much resin because you're creating hollow parts, hollow cavities. Now, the PSLA will not, we do have an answer to producing true silicones, right? But it's an indirect method. It's not directly out of the printer. So remember that you're printing things like an SLA system. So the parts are not hanging in the air. They're supported on a base. So they're sitting on their supports. Now, if we had a rubber material in the vat, the parts would be sitting on rubber supports, so they would collapse. So just because of the geometry of the parts that we're printing, this is not really ideal for filling a vat with rubber material. But again, as I mentioned, we have a solution for our eggshell molding solution that it will enable you to develop quickly roll out true silicone parts.
Okay. The next question is, what is raster based?
Yes, it's the opposite of an SLA system. An SLA system is vector based. In other words, your light source travels on a path, on a pathway, right? It starts at X and it moves to Y across the build platform. So the more lines you have to draw, the slower your layer time is on a typical SLA, right? With a raster-based system, you're essentially using all of your light is thrown into the vat at the same moment, right? So there's no travel distance. The lights are turned on across the entire platform, so the entire layer is cured at once in the resin. That's all it means. So it's just contrasting SLA really with light projection technologies. Light projection is the entire snapshot of your layer is occurs at once, and with an SLA or vector-based printing, it's slow, well, not slow, but there's a travel time, there's a draw time that it takes.
Okay. So the next question is, do you have rubber material in PSLA?
Yeah, I just covered that. Sorry. So yeah, because of the geometries, as I mentioned, because of the fact that you're printing on a tray, this is the one thing that a PSLA cannot do like a DLP. So on a DLP system, you can easily have rubber materials because the parts are hanging off of their supports, right? But on a PSLA, they're sitting on their supports. So the rubber supports would collapse and the part would collapse. Um, so, so no, we don't have 3D printing rubber-like materials on the PSLA. We do have them on the Figure 4 system. We have a rubber 10 material with a shore A of 90, and we have a rubber 65A shore material. So two different rubber materials in black that you can use on the Figure 4. For PSLA, again, as I mentioned, we use the eggshell molding application to create true silicone production parts.
Okay. The next question is, do you have peak available?
Hmm. Well, PEEK is typically uh, an FDM type material that's printed on SLS or FDM printers. Uh, and those are true thermoplastics, right? So the PSLA does not have a peak. We have a range of very tough materials. We have a range of rigid materials. The ProBlack 10 is excellent. We have a range of high temperature materials. So we have a range of production grade tough and strong materials that may be able to simulate close to what your application requires, or hopefully spot on, right?
Okay. Is there any cons of PSLA if we go for more complex parts? How about the cost of the parts, as we need the both quality and pricing for
Mm,
rapid prototyping?
mm, mm. Um, so I think if you're a service bureau and you're constantly producing parts at a very rapid rate, you're going to get a very good return on your investment with the PSLA, thanks to the speed and the user friendliness and the uptime of the system. So I think it's going to be a very cost effective solution. Now, if you're using it just for prototyping, yes, the value proposition is not as strong. And I'll say that's the only the only drawback is if you're using it just for basic prototyping, maybe not. But as soon as you or your customer needs to scale into production batch parts with true production outcomes, the PSLA is able to span that gap very effectively. So I think that's where the real value lies. It's not in prototyping. There are so many systems out there today that you can get at very low cost if you just need basic prototyping. The main thing is, how do we scale? How do we replace tens of thousands of production grade parts from injection molding into 3D printing to save money and save time? And PSLA is the perfect answer really to that. That's where its strong point is.
Okay. The next question is, can investment casting, lost wax casting manufacturers use this for mass production?
Yes, yes, they can. So as I mentioned, we have an eggshell molding material that it also doubles as an investment casting material. Okay, so you can create your investment casting patterns. And again, they're very lightweight. They're basically hollow parts. And we've tested it, and we have an add-on in 3D Sprint. So a special 3D Sprint license doesn't cost very much. And you purchase that, and you're able to use the investment casting, or what we call our quick cast build styles on the PSLA. And we've tested this with a range of investment casting patterns, and it works very well. And that is using the eggshell amber 10 material.
Okay. The next question is there any resin closest to carbon composite material?
Carbon composite. Well, we have two new composite materials. One of them is called rigid composite white, and this is a very, very strong material. It's used in wind tunnel testing by F1 companies. We also have it. We have it in a white color. We also have it in a purple color, but it's essentially the same composition, and it's a very strong, very durable composite resin with an amazing surface finish and texture.
Okay. So our next question, this person wants to know, he wants to elaborate you. So elaborate how it will help the jewelry industry.
The jewelry industry,
Yeah.
well, you'll be able to print your parts very quickly on the platform. So you can probably put a number, I don't know how many, let's say it's rings, you could probably be able to print 100 rings flat on the platform instead of hanging them in the air with multiple supports. So you can use far fewer supports on a PSLA if you're printing them on a flat platform. So I think that's the main benefit. So you'll get DLP speeds, but without the need for support removal. I think that's the main advantage. But again, we have to check benchmarking what is the correct material that we can use on the PSLA.
Okay, the next question is SLA resin-based printer is an advantage when compared with metal printer in applications with plastic or sheet metal castings?
Oh, I don't understand. Sorry, say that again.
Uh, is SLA based printer is an advantage when compared with metal printer in application with plastics or sheet metal castings?
I don't know. I don't understand that question. I'm sorry.
Um,
I don't understand.
Sam, I've assigned, if you can read on that question, we have assigned it to you.
Okay, I'll have a look at it. But
Yeah,
let's move on. I'll try and get back to that one.
yeah, sure. So I'll assign you another question till then. Okay, so the another question is
Oh
if
yes, I can.
resin.
I can. Sorry, I can answer this one. Now I'm reading it in the notes. So
Okay.
the SLA resin-based printer, does it have an advantage when compared with metal printers and applications like plastic or sheet metal casting? So look, metal printers are incredibly expensive, first of all. Um, if you need to produce a highly complex metal part that cannot be replicated in the investment casting process, then you need a metal printer. Okay, there's not really, especially if you want it to be lightweight and you want it to be optimal strength to weight ratio, then you really need a good high-end metal printer. We have a lot of them in 3D systems. But if you need to produce cost-effective, simpler metal components, then a resin printer using investment casting is often a better answer than a metal printer. You'll be able to rapidly turn out patterns that can be sent to a foundry to produce cost-effective metal parts. And we've done this with many customers in the past. Um, Machinery production companies where they need to replicate brackets or broken parts that break easily on some of their machines. And they've used the investment casting in the resin printer to produce quite cheap castings. I hope that answers that. Hope that answers that question.
Okay. Moving on to the next question. If resin had closer strength of use as substitute to steel or aluminum used as a functional part of machine.
Oh gosh. Hang on, let me see. I'm just reading the question. If resin has closer strength of use as substitute to steel or aluminum used as functional parts of machine? No, I don't think so. I don't think so. I don't think you'll be able to substitute steel or aluminum with a resin part. I don't think it has the strength. Even yeah, I don't think so. I don't think so. You'd need a carbon reinforced part at the very least to be able to simulate steel or aluminum in a functional machine. Okay.
Okay, so one more question. So I guess this is last one. Can we print glass items or any transparent material similar to glass?
You cannot print glass. Glass needs very different processes, very high temperatures. No, so we cannot print glass. We do have, or we will have coming, I hope very soon, a water clear, transparent resin that will be able to simulate um, uh, PMA or polypropylene plastic bottles transparent, water clear, transparent bottles and plastics. Watch this space, coming soon. No promises for now, but we hope it's coming soon.
Okay. So got one more question. Can resin replace for ceramic alloys?
Gosh, that's a difficult question to answer. Probably not. Probably not. If it's a ceramic-based alloy, no, I don't think so. But that would be a question for our material experts, if at all. I'm sure we could find something that would something in our additive landscape that would be able to answer such a question. But maybe it's not a resin.
Okay. We are getting couple of questions more. Can we print rubber part like P20 material in PSLA?
I did mention previously that we cannot really print successfully digital rubber parts in the printer. We can create the molds to produce true rubber parts. So if you have a specific rubber formulation that you are using, you can create the mold for those rubber parts very quickly on a PSLA.
Okay, the next question is 90 micron is the native pixel size. Is there a dynamic pixel size?
We do not have a dynamic pixel size, but we do use, so we do not use pixel shifting, but we do use our grayscaling to produce more than adequate results. In fact, you could see the results. Very little aliasing, very little stepping effect, and fantastic down-facing surfaces.
Okay. The next question is Stuff Clear compatible with PSLA yet?
In theory, it's compatible, but we haven't qualified this material because we want to produce a better material in clear for PSLA. So again, watch this space. We are working on a more advanced formulation that will produce a better clear outcome for PSLA.
Okay. I think we have completed the questions for today. So thank you, Sam. Thank you for answering all the question. And as
Pleasure.
we wrap up, sorry, Sam, did I cut you off?
No, I just said pleasure. Thank you.
Okay. As we wrap up today's webinar, a heartfelt thank you to Sam Green and the 3D System teams for sharing their expertise. Also, thanks to the entire Shree Rapid Technologies for putting lots of efforts in this. And importantly, thank you for the audience for joining us. So before you go, we would like to hear your feedback on this today's session. So once the session is over, please do share your feedback and answer the questions on basically so we could understand what we need to improve and whether this content was appropriate to you and what we can bring to you in future. Feel free to connect with us at marketing @shree-rapid.com or call us at the given number flashing on your screen for anything related to 3D printing solution and services. We hope to see you again in our upcoming webinars and take care and have a great day. Thank you everyone.